Okay, so this is NCCER Instrumentation 2 Module 10, Layout and Installation of Tubing and Piping Systems. Everybody should know that is a picture of on the board by now. This is a P&ID drawing. So just remember that these show the interconnections between different pieces of equipment, but not necessarily how everything is laid out. So this just says how it's connected. So trade terms. You'll have, you know what ASID is. ASME and ASTM, American Society of Mechanical Engineers, American Society for Testing and Materials. Those are just what everything is going to be, the rules and regulations that stuff has to follow. So you'll have, so you got acid, caustic. Definitely need to know that you should know the difference between those. We'll talk about fluid hammer with getting starting and stopping stuff. If there's still air in the lines, you'll get fluid hammer. Packing gland, you've packed a valve by now. Yep, so page 1, my first highlight, the second paragraph, first sentence is highlighted. The first step in the construction of any job, any object, first step in construction of any object is planning. In context of tubing and piping, the planning procedure is referred to as layout. So if you're planning piping and tubing, it's considered the layout of the piping and tubing system. Moving on to page 2, you can see all the piping and tubing for and conduit installation for that picture right there. There's a lot. I don't have that picture on the board, but you got that picture on the top of page 2. Like a lot of neatly done piping and tubing and stuff like that. Looks like a fairly new installation. Nothing highlighted on page 2, but going into page 3, 111, layout preparation. So you have drawings, so that's where your P&ID comes in. You got that same P&ID on the bottom of page 3. In the drawing section, pretty much the first paragraph and a half are highlighted for 2 different highlights. So first paragraph is 1, the diagram, also known as the piping and instrumentation drawing, P&ID. It's on the board, bottom of your page, is usually the initial drawing in the piping design process. This document shows the equipment in the system, the instrumentation requirements, and the piping connections between the major equipment. The P&ID shows the required supporting services that impose design requirements on the system. Out to the side of that paragraph, I wrote data for all instrumentation loops. So this has the data for all the instrumentation loops. The next paragraph, first sentence is the highlight. The project piping specification, so key in on project piping specification, is a document that defines the complete system design. Operating pressures and temperatures, key in on that. So you need to know the operating pressures and temperatures are found in the project piping specification section. Piping materials, pipe wall thickness or schedules, types of fittings, and other various installation requirements. You just need to know operating pressures and temperatures are going to be in your process piping specifications. Continuing on, last paragraph on the page, it starts in the bottom left. First sentence is highlighted. Isometric drawings, which is what you have in figure 3 on page 3. Are proportional representations in which the images are typically rotated 45 degrees and tilted down slightly more than 36 degrees and drawn to scale. So that figure 3 is an isometric drawing, so you can kind of get a 3D visual of how stuff is laid out. Immediate next sentence in the top right of 3 is also highlighted. Isometric projections are particularly useful in drawings for layouts in which the piping or tubing is bent in more than one plane. Kind of gives you a 3D view. Moving on to page 4. Codes and standards, that talks about the ASME or the ASTM, different Standards, no highlights in those, but you just need to know that those standards have to be followed. A lot of piping and tubing, like boilers boilers can be big bombs if not treated with caution. So there's different standards you have to do when piping up a big boiler. Nothing in visual inspections. Going on to 120 considerations in the layout of a piping system. So they have all the different things you have to consider: obstructions, routing, proximity to other hazards, thermal expansion and contraction. They'll go through all the different sections for all those different bullet points. 121 obstructions, visible and future. The first two sentences are highlighted. When laying out piping, fitters must avoid interfering with other structures and utilities in the plant, such as other piping systems, structural members, HVAC ductwork, and electrical conduit. Avoiding obstructions can be especially challenging because fitters must meticulously inspect existing obstructions and anticipate other obstructions that could occur in the future. Down below, 121, right above where you see the page 4, where it says page 4, I wrote in there, plan to avoid current and future obstructions. It's happening over and over again. I know people that have you put in instrumentation, refrigerant lines, or something like that. Next part of construction, somebody comes in and has to do something to the roof, and those instrument lines have to be moved. So that's poor planning. Like, you have to have a plan, like, this is going here, so my instrument lines can't run here. So you have to. It almost looks like you're going around something invisible, but that's so that another piece of equipment can be installed. So you always want to make sure you have all the information when installing different lines and stuff like that. Immediately after that highlight, I've got 2 more sentences as a separate highlight. In the initial design phase, engineers have used composite drawings and plastic models to aid in the task of making a comprehensive assessment of both visible and future obstructions. Today, three-dimensional computer modeling is frequently used instead of plastic models. That's self-explanatory. Preferred routing, 122. Second paragraph, right after where you see the NEC, so like I guess it might be the second sentence. Online test question. For example, a minimum headroom of 7 feet measured from the lowest point of the piping should be maintained in pedestrian areas. Obviously, you don't want to put a pipe at 5 foot that people are going to walk into if they're in a pedestrian area. It has to be a minimum of 7 feet in pedestrian areas. Page 5, last paragraph on the page, has to do with the picture that's on the border at the top right of page 5. Install control valves with the valve stem in the upright position. So you want the valve in the upright position. This does not mean it has to be directly 90 degrees upright. You can turn this one bolt pattern, because if I put this here and another pipe over it, that valve stem is not going to open up all the way, because the valve stem is going to hit the other pipe. So you have to watch that when you're installing this. You install this all the way, somebody has to go back in, remove all these bolts, twist this one notch to the left or right, and then reinstall all the bolts. But you want that in the upright position because you don't want stuff leaking into your control valve. Moving on to page 6 and 7. They show different control valves and check valves, pressure relief valves. You got different types of valves you can put into this stuff. I have no highlights on pages 6 and 7 as far as going in any more of the preferred routing stuff. No highlights on pages 6 and 7. 1, 2, 3 talks about proximity to hazardous elements. Nothing highlighted in that. Also, you want to watch when you're installing different piping and tubing next to hazardous elements. Page 8 and 9, piping sag. If you don't support your pipe often enough, it's going to sag. No highlights in that. 1, 2, 5, thermal expansion and contraction. You can see the high pressure expansion joint on page 9. So this can actually expand and contract based upon temperature changes. As temperature changes, stuff expands and contracts. You can also use these expansion bends So U bend, circle bend, double offset bend. Excuse me. These different pieces of instrument tubing can expand and contract based on the pressure and temperature that's inside them. I don't have any highlights on pages 8 and 9, but just know that this stuff is here. Venting and drainage requirements. Nothing highlighted on that. You need to be able to drain different instrument lines. We've talked about that. Page 10, bends and connections. So this is important. You have to have different radiuses for your bends and your connections. This is like a 5.5 inch radius in this bend. They talk about the different bad bends. So this is flattened. So this is not used in the right die, more than likely, or kink. This looks like it was tried to bent and then rebent and then wrinkled bend. Again, wrong die is usually what causes wrinkled bends. 127, bending connections. The last sentence on page 10 is highlighted. The ideal bend radius can be defined as a bend with a radius approximately 2.5 to 3 times the outside diameter of the pipe, as illustrated in figure 13. So my pipe diameter up here on the board is 2.25. 2.25 times 2.5 to 3. So 2.25 times 2 is 4.5. Times 3 is 6.75. So 5.5 to 6.75 has to be your radius for that bend. Non-piping system obstructions, 128, nothing highlighted in those. 130, developing an isometric sketch. Going on to page 12 and 13. Third paragraph on page 12, first sentence is highlighted. To more easily freehand sketch an isometric drawing, start with a sheet of engineering paper or graph paper that is evenly divided into smaller squares so that the scale can be applied. Right hand side of the page 12, second to last paragraph, first sentence is also highlighted. After determining where the tubing runs must connect, the fitter performs a walk through the locations where the loop is to be placed. That's just to make sure there's nothing obvious that they're missing when engineers are doing drawings and stuff like that. Highly, highly recommend. Go look at the actual stuff, because stuff might have been moved and whatnot, and it's not on the original drawings. Go look. They go through the steps on developing an isometric drawing. Starting on page 13. In step 1, on the right-hand side of page 13, that first 2 sentences on the right-hand side are highlighted. Finding the length of a 45-degree line segment representing these runs requires using some fitter's math. Subject of fitter's math was covered in detail in another module. Out to the side of that highlight, I wrote, developing an isometric sketch requires the use of fitter's math. So remember, you're using that right triangle math in order to develop these sketches. They go through the steps on doing the math. Page 14, the only thing I've highlighted in these steps is the sentence right after apex on the right-hand side of page 14. The apex is the starting point of an angle. I'm not going into that too much. 16 and 17, complete the steps for creating an isometric sketch. Nothing highlighted to finish out those steps. Moving on to 140, bill of materials. We talked about a bill of materials and how it's nice to have a bill of materials even whenever you're doing maintenance on different stuff. 140, second sentence or last sentence on page 17 is highlighted. A bill of materials is typically included on the instrument installation drawing as shown in figure 28. So figure 28 is not what I have on the board, but page 18 shows an instrumentation installation drawing with a bill of materials. So those are nice to have together because you have your isometric drawing that shows the installation, and then it points out what each piece of equipment is in the bill of materials on the right. Page 19 just shows the bill of materials. First sentence on page 19 is highlighted. Bill of materials, figure 29, lists all the items that are needed to properly install the particular instrument and any instruments identical to it. Skip a sentence and the rest of the paragraph is highlighted. The bill of materials also describes fittings or fitting and connection requirements, including the sizes, quantities, the materials of which the fitting and connections must be made. A lot of this stuff, look in the material 316, stainless steel. Like that's a grade of stainless steel. All this stuff has to be stainless steel. So you can't put stainless steel in a brass fitting because the brass isn't hard enough to swedge onto that stainless steel tubing. With your ferrules. Ferrules is the word I was looking for. Your ferrules aren't hard enough to swedge onto stainless steel if they're brass. Brass is a lot softer than stainless steel. You've got section 1 review on page 21. I'm going to continue on to section 2. Pull up this. Section 2 is going to go through measuring the tubing and stuff out, which is a lot of this, like determining the gain and stuff like that, is going to be done in the lab when you're doing your tubing lab and stuff like that. If you didn't already meet with, a lot of times we bring in a presenter from Swedgelock, and you do a tubing demonstration during that presentation, which is very beneficial. If you have the opportunity to even go to one of those, make sure you go to that. 210, determining initial bend position and angle. First sentence is highlighted. Before bending tubing, determine the distance to the first bend and the angle of the bend. Duh. Tubing gain. So this is gain. If you haven't heard gain before, gain is like you're walking down the street right next to somebody else. They're on your inside. You're walking straight, and then you turn the block. Whenever you turn that person on the inside, I cut through the grass or something like that. But that they are walking a shorter distance than you walking on the outside. So if you're doing a 90-degree bend, when you cut that corner, you have gain than going all the way straight and then turning. So you have to determine your gain when bending tubing. In 211, tube gain. Second paragraph is an online test question. A good rule of thumb for most standard tubing materials and radius blocks is that the tubing will gain approximately 1 tube diameter for every 90 degrees of bend. There's also tube gain charts that you can see on page 23 to determine actual gains. Last paragraph on page 22, first sentence is highlighted. The precise amount of gain is related to the diameter of the radius that is used. Talks about table 2, provides that. But yes, you have to determine your gain before bending your tubing. Pre-measuring. They can go, like good tubing fitters can go in and take their measurements and make sure they have enough tubing. Nothing highlighted in that. 213, marking the pipe. Second sentence is highlighted. Use a ferrule or a wraparound designed for assembling compression joints as a guide to make measurement marks all the way around so the mark is always visible. So you're marking all the way around the pipe. Usually you're doing this with a pencil. They show it with a pencil. That way, after you're done bending everything, you take your finger a little bit of cleaner and wipe your lines off. It looks a little bit more professional. Second to last paragraph on the page, on the right hand side of page 23, first 2 sentences are highlighted. When measuring with a measuring tape, do not use the end of the tape as a starting point. The end of the measuring tape gets damaged over time and can lead to measurement inaccuracies. They usually call that pulling an inch. So if you look at this picture right here, they pulled an inch. So they're not starting at 0, they're starting at 1, and say this pipe goes all the way to 12. This pipe's not 12 inches long, this pipe is 11 inches long. Or they're measuring to 5, this is 4 inches between 1 and 5. If you're marking your stuff right there. Pulling an inch. It just makes for a more accurate measurement. Last paragraph on the page, first sentence is highlighted. The center line of the piping or tubing is the basis for all line measurement. Whenever you're doing drawings with tubing and piping, you're taking your measurement from the center of the pipe. That's important, especially depending on what size pipe you're using. Page 24, determining pipe length. Second sentence is highlighted in 214. The simplest method to accomplish this is the shoulder-to-shoulder method. Simplest method to accomplish determining pipe length is the shoulder-to-shoulder method. 220, bending tubing. Second sentence is highlighted. Hand benders, called one-shot benders, are usually designed to bend only one size of pipe or tubing. These are hand benders. So usually you're bending with these. You can't bend and then rebend or anything, but these are compression hand benders. The second two sentences, or the last two sentences of that first paragraph in 220 are also highlighted. To bend different sizes of tubings, fitters must separate hand benders for each size of pipe and tubing. These sizes are marked directly on the bender. So if I scroll in here, this is for 3/4 inch tubing. This is for 7/8. This is for 5/8. These are most of the time, not always. I will say there are some hand benders that can bend a couple different sizes of tubings. They don't work as well as one that only does one size of tubing. So if you're doing this stuff all the time, use one that only bends one size of tubing. Make sure you get a good tubing bender. Swedgelock makes a good one. Rigid makes a pretty good one as well. Those are the two that I've worked with the most. Still on page 24, in that warning on page 24, first sentence is highlighted. Using too small a shoe on a hydraulic power bender can cause the shoe to explode under the high hydraulic pressure. Make sure, I've never used one of these hydraulic benders, but if you're using one of these, make sure the shoe that you're building, like that looks like huge, like that looks like 4-inch tubing or something like that. So they can actually bend that tubing with a hydraulic bender, but make sure that stuff is sized correctly, because bad stuff can happen. Goes through the steps on using a compression tube bender, 221, starting on page 25. In step one, I've got a highlight in the third, I think it's my third, 1, 2, 3, fourth sentence in step one is highlighted. Based on the direction from which the tubing was measured, align the mark made on the tubing with the mark on the slide block. That's like step one when going through. Mark your tubing. Depending on which way you have your reference point is, that's where you'll use your L or your R. So their tubing is marked aligned with the L because the reference point is on the left, depending on the direction from which you measure. It goes through the steps on that. In step 5 goes into page 26. I've got right after, on page 26, right after where you see spring back, I've got the rest of the step highlighted. Harder materials tend to spring back very slightly towards straight, therefore the bend may need to continue 2 or 3 degrees past the 0 and 90 degree marks. With soft tubing, such as copper, the opposite situation occurs. It is usually best to stop copper tubing roughly 3 degrees before the two marks are aligned. Copper tubing, you bend a little bit less. Harder tubing, stainless steel, you bend a little bit further. You're going to have a question come out of table 3 on calculating gain. I think they give you the gain table on the practice test, and they just ask you the gain for a certain size and bend radius. Should be easy to figure out. That's the end of section 2, so I've got a section 2 review on page 29, continuing on to section 3 on page 30. Let me get my last PowerPoint up. So, supporting tubing and piping. Got to make sure you do that. A lot of stuff vibrates, comes loose, moves around. You've got, again, they talk about snubbers again in this section. You've got static loads, thermal growth, different stuff that's going to affect supporting this piping. First paragraph, third sentence is highlighted. One of the most commonly used and most stringent of these codes is the ASME, Boiler and Pressure Vessel Code. Like I said previously, Boilers can become bombs. Boilers can blow up if pressure is not treated right. So they are very strict in their AS&E standards of boiler codes. Like I've been around boilers quite a bit, and like even to work on one, like you have to be trained and certified. Don't go just working on a boiler if you don't know what you're doing. 301, weird section. Support spacing, so how far you can go with supporting different hangers. Third paragraph, first sentence is an online test question. 301, third paragraph, first sentence, online test question. Where there are concentrated loads due to heavy components installed in the piping system, place supports as close as possible on each side of the load. Closer to the supports, the more weight they can handle. Recommended hanger spacing is on page 31. You can look through that table, no highlights on page 31. Tube and pipe hangers and supports, 310 going into page 32. Constant supports, you can see those in figure 41. So you can see like this, you'll have a support to the structure, and then this just takes, like if it vibrates or something like that, it can spring, so you have a constant support. Nothing highlighted in that. Rigid hangers and supports. You got different types of hangers that can be hung from all thread and pipe clamps or beam clamps hung from the ceiling. Used a lot. You'll see these a lot for like fire systems. So you have rigid supports. Nothing highlighted in those, but you can see there's a bunch of different types of clamps with different amounts of bolts depending on what you're doing. Snubbers, again, you should know what a snubber is. I think we covered them in the last chapter. Just protects your stuff from growth. This last paragraph on page 33, first two sentences are highlighted. A snubber resembles a rigid restraint. However, it contains a mechanism that permits movement in the presence of slowly applied loads but locks during rapidly applied loads. I think they have a hydraulic snubber. So this is I guess this is a little bit different than the snubbers we talked about for instrumentation. So this is just to prevent stuff from shaking a lot. So it has a piston inside of a cavity that's filled with oil. The oil can move back and forth through your ports, but it's not going to move super fast. So this stuff can expand and contract and is slower. Than just like a spring. Page 34, last paragraph, last one sentence paragraph on page 34 is highlighted. Mechanical snubbers work in a similar fashion, except they use a gear and pinion designed to produce the same effect as the hydraulic snubber's piston and cylinder arrangement. So they can have mechanical snubbers that aren't hydraulic. A lot of times in food industries and stuff, you can't have anything hydraulic just for the threat of it getting into the food or anything like that. 320, supporting structure. Second sentence is highlighted, 320. Generally speaking, if tubing runs are less than 3 feet in length, the tubing can be considered self-supporting and no additional support mechanism is required. 3 feet and under doesn't have to be supported. The rest of that paragraph is a separate highlight. For leaks exceeding 3 feet, however, it's recommended that tubing be supported every 3 feet at a minimum. Right after that, you've got bullet points. Follow these recommendations for tubing installations and tubing support. I've got the fourth one highlighted as an online test question. Be aware of potential tubing vibration and support the tubing to prevent or reduce vibration. One method commonly used to guard against damage caused by vibration in structure support is to bend a loop in tubing. This is called a vibration loop or a pigtail. More often than not, they've done helical loops, but they've learned that a better way of doing is actually doing, I can't remember the name for it, but they do square loops. If you've watched Brian with Squedgelock, he showed how they do square loops, and that takes out some of the vibration in the total length of the tubing. So the whole pipe isn't shaking, just that one area is. can dampen the damage to the whole pipe, or it can prevent damage to the whole pipe. Top right of page 35 in tubing support hardware 321. Top right of page 35, that sentence all the way in the top right. Unlike most piping and conduit, tubing requires protection as well as sufficient support to prevent flattening, nicking, or minor damage to the outer walls. This is for outer walls that can eventually lead to cracks and potentially dangerous leaks. So you have to have protection from outer wall damage. Last paragraph before 322. I've got 2 questions that come out of the whole last paragraph. Whole last paragraph's highlighted, 2 questions that come out of it. Older style tubing support devices often did not provide cushion protection against outer wall damage. Many of these supports are still in use today, but they are gradually being replaced by the newer cushion supports. Examples of non-cushion supports are illustrated in figure 48, including gang clamp, one-hole clamp, and yoke clamp. So they have a bunch of different tubings. You can see the cushions inside of these supports. 322, support trays and channels. First sentence is highlighted in 322. Tubing can be placed on piping racks using a channel system such as Unistrut. Unistrut, I don't have a picture. Oh yeah. Unistrut is this stuff in the bottom. Very versatile piece of strut system, which you can use to mount a bunch of different stuff. Page 36, sentence that splits the columns is highlighted. Many times the tubing will share the same tray with instrument cable and be divided from the cable by a partition in the tray. You have to have a cable partition if you're running instrument lines as well as instrument cabling in a cable tray assembly. That is all my highlights for Module 10 of Instrumentation 2. So you've got Section 3 review, Module review, and a practice test to do for Module 10.